In today's lesson, we are going to look at finding the maximum or minimum of a quadratic function. So this should be a little bit of a review. Hopefully you've looked at some of this in grade 10. You've definitely looked at some of these concepts in grade 10. Maybe not so much finding max or min, the max or min, but it's not too far off of the concepts that we've already looked at. So just a little bit of review. We kind of talked previously about the vertex form on all the different forms. So this might be a little bit of a speed run, but we did talk about this in a previous lesson. And again, you should know some of this from grade 10, or you did learn it in grade 10 anyways. Whether you remember it might be a different story. But our vertex form gives us some pieces of information. It does tell us our vertex, which is H and K. One thing to note, the H value, we have to change the sign. It's the opposite of what we see. It also tells us the axis of symmetry. The axis of symmetry is basically a vertical line that cuts our graph or parabola in half. And in our case, it's x equals h. Again, we have to make sure that we change the sign on the h. It also tells us whether it opens up or down and the step pattern. And that all deals with the a value. The step pattern is 1a, 3a, 5a. And if a is greater than 0, it opens up. So it looks something like this. So if a is positive, it opens up. If a is less than 0 or negative, it opens down. So we do get a lot of information from this. So if I was to look at this graph here, the one that's shown, I can clearly see the vertex at the point 2, 3. So in this case, I at least have y equals x minus 2, opposite, squared plus 3. For the a value, I'm just going to move this out of the way. The a value is the step pattern. And in our case, the step pattern, we start at the vertex, we always go over 1, and then we go up or down until we hit our quadratic. So in this case, the first step up is 1. And then to take a step over again, always one step over, and I go up until I hit my graph, and it would be a step up of 3. So you can kind of guess what the next one is going to be, even though we can't see it. It would go up, and it would go up 5. So that means my step pattern is 1, 3, 5. And realistically, with the step pattern, all we need to find is the first step, and that will tell us the a value. So in this case, our a value is 1. We can also see the axis of symmetry. Right, it is an imaginary line. In this case, it's x equals 2 that cuts our parabola in half. Factored form, again, a value. So a is the same as other forms, which it will be for all of them. So a is the same for other forms. The other thing that we get, r and s are x-intercepts. So that is the unique thing about this form. It tells us the x-intercepts. We just have to make sure that we change the sign as well. So we need to change the sign of the r and the s from what we see in the brackets. So in this case, if I were to look at this graph, I see two x-intercepts, -3, 0, 2, 0. So that means so far in my equation, I would have x plus 3, x minus 2. The order of that doesn't really matter. It might be useful to have it left to right, but it doesn't really matter what order you put it in. It wouldn't be wrong if you had -2 first and then +3 for the second one. To figure out the a value, we want to kind of approximate what the step pattern is. So I go over 1, up, and it looks like I'm going up about a half. Go over 1 again, So I go up a half, 1.5. So again, this one's not the nicest because we can't really tell too much. But I will tell you that you were going up at least 0.5, 1.5, 2.5, which means that our A value would be a half. I can at least approximate that from at least the first step anyways. After that, it does get a little bit messy. I can approximate at least a half, so that would be my equation. Standard form doesn't give us a lot of information. The C value is the y-intercept, so that might be useful in some cases. Our initial value, well, not our initial value is not a linear relationship, but it does tell us the y-intercept. We can use the quadratic formula. So we can use the quadratic formula to find the roots or the x-intercepts, right? So if we want to use the quadratic formula, we would have to put it in standard form. As well, one extra thing, we can find the x value of the vertex by doing negative b divided by 2a. So that gives us the x value of the vertex. So realistically, if we wanted to, we could kind of go through, find that, plug it back in, and so on. But we see our y-intercept here of 0, -2. So at least we know somewhat in our equation ax squared plus bx minus 2. So we at least know part of it. Right? So that's why the standard form isn't quite that useful. The other two are more useful. There's more stuff there that we can actually use in terms of our quadratic. So before we get into finding the max and min, we want to take a quick look at perfect square trinomials. And we are going to be using these when we try to find our max or min. Right? So with this, the first and last terms are perfect squares. So in a perfect square trinomial, the first and the last terms are perfect squares. So in our examples that we see here, our general forms, we're talking about these two values. The middle term is basically 2 times the square root of the first term times the square root of the second term. So that middle term follows that pattern. And that's what we want to look for to make sure it's a perfect square trinomial. So for example, I want to factor each of the following. X squared plus 24x plus 144. Should check first that it does fit the pattern. So if I take the square root of the first term, square root of the second term, I should get perfect squares, which I do. Then I want to check that if I take those two values, multiply them each other, and then multiply by 2, do I get my middle value? In this case, I do. I do get 24x. So this fits. This fits the pattern of a perfect square trinomial, so I can factor it as such. And when I factor a perfect square trinomial, take the square root of the first term, square root of the last term. It's going to be squared in one bracket. The sign between the first and the second term is going to be the sign in my bracket. So this becomes x plus 12 squared. And that's it. So for the next one, again, let's just do a quick check. X squared, square root of that is x. Square root of 81 is 9. X times 9 times 2 is 18x. Now, when we're testing this, all we're concerned about is the number. Do we get the right number? Which in this case, we do. So we get 18x. I'm not too concerned about the negative. The negative is going to tell me what the sign is. So the square root of the first term, square root of the last term, the negative or the sign becomes the negative in our factored form, or when we factor it. So that's a quick overview of factoring perfect square trinomials. Next, we want to see, can we make the following perfect squares if we're given the middle term and the first term, can we find or can we make a perfect square? Well, we kind of have over here, the last term of a perfect square is half the middle term squared. So if I look at the middle term for the first one, half of the middle term, 10 divided by 2, and then squared, is 25. So if I make the last term in this trinomial 25, it now becomes a perfect square, and I could factor it as such. With the last one, negative 24 divided by 2 squared, so negative 12 squared is 144. So if I make the last term 144, I could factor it as a perfect square trinomial. And we want to know how to do this or know this relationship because it's going to be useful when we're trying to find the max or min. So with finding the max or min, there are two ways to find the maximum or minimum: completing the square and partial factoring. So with both of these, or at least with the first one, completing the square, the goal is to go from standard form to vertex form. So we get y equals ax squared plus bx plus c, and we want to convert that to vertex form. And in vertex form, we do see a perfect square trinomial, this x minus h squared. So that's where knowing what a perfect square trinomial is going to come into play. And once we have the vertex form, the max or min point is simply from our vertex, h and k. Specifically, it is the k value, right? It is the k value where we're concerned about the y value. Max or min deals with height or the vertical value. So we're concerned with the k value of the vertex. So completing the square. We've looked at this in our review. We have kind of the steps here, right? We'll walk through those steps as we go through. We're going to put brackets around the first two terms, factor out the number in front of the x squared, look at the last term in the brackets, divide it by 2 and square it to make a perfect square trinomial. I've heard this, or I've been referred to this before, as finding the magic number. So the number that makes it a perfect square. We then add and subtract that term behind the last term in the brackets, move the negative term outside the brackets by first multiplying it by the a value, simplify the terms outside the brackets, and factor the perfect square trinomial. So it's a lot of words. Let's actually just see this in action. Let's go through an example. So example 1. Convert the following equation into vertex form by completing the square. So first, we need to put brackets around the first two terms. Done. Next, we need to factor something out. Factor out the value in front of x squared. In this case, there isn't a value in front of the x squared, or it's a 1. So I can't really factor out a 1. It's not going to change anything. So I'm going to leave it. So x squared plus 8x. The next step is to find my magic number. And that's going to be using that last term, that 8. So what I want to do is I'm going to take the 8, divide it by 2, and then square it. I'm going to get 16. That's my magic number. That's the number that I'm going to add and subtract in my bracket. And I'm going to still have the plus 5. Next, I want to move this negative term out. So if I move that negative term out of the bracket, I need to reapply a factor, which I didn't take out, so I don't have to do anything extra. I'm going to move the negative 16 out. I get x squared plus 8x plus 16 plus 5 minus 16. So that minus 16 is now outside the bracket. And the reason we add and subtract is, one, we're trying to make a perfect square trinomial, but if I add a value and I subtract the same value, they cancel each other out, essentially. So technically, I haven't really changed the equation, right? If I add a value and subtract a value, they cancel each other out. I haven't done anything to change it. even though it looks different. And finally, the last step, I can simplify the outside and I can factor the bracket as a perfect square trinomial, which it should be. So x will be the first term. The last term will be the inside of the bracket, so this 8 divided by 2, or the square root of the last number, so 4, and the sign between the first two terms will be the sign in the bracket, so plus 4. That will be squared because it's a perfect square trinomial, and I simplify the outside. 5 minus 16 is negative 11. That is now my my equation in vertex form. So now I can use that to help answer what is the vertex in the axis of symmetry. Well, the vertex is my h value, or the opposite of what I see, so negative 4, negative 11. The axis of symmetry is x equals negative 4. And is it a maximum or minimum? Well, in this case, it is a minimum point because it opens up. So it opens up because the a value is 1. So that means my graph or my parabola is going to look something like this, with my vertex being at the bottom. So it's a minimum. So I do need to look at what the a value is, the coefficient, to tell me whether it opens up or down. If it opens up, it's a minimum. If it opens down, it's a maximum. Let's go through example 2. This one's going to be a little different because when we put brackets around the first two terms, we see that there is a value that we can factor out. So I can factor out a value, and I'm only going to factor out a value. I'm only going to factor out a value of 2. I'm not factoring out the x or anything like that, just the value that's in front. So just 2. I'm left with x squared minus 6x plus 11. I'm going to find my magic number. So I'm going to take that negative 6, divide it by, oops, keep it color coded. Take that negative 6, divide it by 2. How did I color code the last one? Oops. Let me just keep it color coded. So negative 6 divided by 2 squared. That's negative 3 squared, or 9. So that means I'm going to add and subtract 9. So x squared minus 6x plus 9 minus 9. Oops. Plus 11 outside the bracket. I want to move this minus 9 out. When I move it out, I need to reapply the factor. So because I took a factor of 2 out, I need to reapply that on this minus 9 when I move it outside the bracket. So that means I need to multiply the negative 9 by 2 when I move it out. So I get y equals 2 times x squared minus 6x plus 9 in brackets plus 11 minus 18. I can then factor the bracket as a perfect square trinomial. So x minus 3 squared, and then 11 minus 7 is, 11 minus 18 is negative 7. This means my vertex is positive 3, negative 7. My axis of symmetry is x equals 3, and this is a minimum point because it opens up, because the a value is 2. So I want you to try to do example 3 on your own. So I'd recommend pausing the video, try to do this one on your own, go through kind of the same steps. I will give you the hint that when you put brackets around, you will need to factor out a negative 3. So I'll give you that starter and let you work from there. Complete the square, find the vertex, and determine whether it's a maximum or a minimum value. This one might be a little bit tricky because we're dealing with some fractions. You could convert to a decimal as well. I left mine as fractions, so your answers might be slightly different if you were working with decimals. But you should have factored out the -3. As I mentioned, I gave you that kind of starter. Your magic number should have been 9/4 or 2.25. Make sure, so when you add and subtract that and you move the negative value out, make sure you reapply the factor of -3. So that -9/4 needs to multiply by -3 when you move it out. So you get -13 plus 27/4 or -13 plus 6.75. When you factor the brackets, you should get a perfect square trinomial of x minus 3/2 squared. And when you collect your like terms on the outside, you should get -25/4 or 6.25 or -6.25. Our vertex then is 3/2 or 1.5 and -6.25 or 3/2 and -25/4. The axis of symmetry is 3/2 or x equals 3/2 or x equals 1.5. And then it is a maximum point or a maximum value because it opens down, right? So the a value is -3, meaning it opens down. So that means it is a maximum. The next step is partial factoring. So partial factoring is another way to find the maximum value or the vertex. And it is a little bit different kind of setup. So we look at the constant term in the expression, right? The y equals ax squared plus bx plus c. So when we look at the constant term, we're looking at the c value. We want to set y equal to that c value. So essentially it'd be c equals ax squared plus bx plus c. And the idea is that so we can cancel out the c values and make it essentially 0 equals ax squared plus bx. We're then going to common factor whatever's left over, set each part equal to 0, and solve for x. And similar to how we would if we're finding roots, but we're not finding the actual roots. These are just imaginary roots, right? So they're not the actual roots, they're just imaginary roots. They're just x values that have the same y values, and they're on equal distance on either side of our axis of symmetry or our vertex. Once we find those two imaginary roots, we find the axis of symmetry, so finding the middle value, and then we use that to plug back into the original equation and solve for y. So again, we'll take a look at this, and we'll take a quick look after at a Desmos, at a few graphs, just to see why this makes sense and why we can do this. So let's use partial factoring to find the vertex and state if it's a maximum or minimum. So I'm going to set y equal to -6, this constant. So -6 is equal to x squared plus 2x minus 6. That cancels each out, or the 6 is out, because if I add 6 and I add 6, they're both gone. I'm left with 0 equals x squared plus 2x. Now I want to common factor this. So 0 equals just x and then x plus 2. Now that I have each, now that I've factored it, I'm going to set each equal to 0. So x equals 0, x plus 2 equals 0, and solve for x. One's already done. The next one becomes x equals -2. These are my imaginary roots. They're not the actual x-intercepts, but they are on either side of my axis of symmetry. So I can find the axis of symmetry, which would be x equals these two values, so 0 plus -2 divided by 2, which gives me -1. So that tells me that's the axis of symmetry, or the x value of my vertex. I can then use this and substitute it back in. So y equals negative 1 squared plus 2 times negative 1 minus 6, and I get y equals 1 minus 2 minus 6, or negative 7. So therefore, my vertex is negative 1, negative 7, and it opens, or it is a minimum point because it opens down. Again, it opens down because the a value is 1 or positive. So that, or not opens down, opens up because the a value is positive, so it's a minimum point. Let's look at the next one. Technically we would set y equal to 3 and then cancel it out. We could just, if we know we're going to do that, let's just get rid of it right at the beginning and set it equal to 0. So 4x squared minus 12x equals 0. Common factor, and common factor out of 4x, and I get x minus 3. Set each equal to 0. 4x equals 0, or x equals 0. X minus 3 equals 0, or x equals 3. I can now find the axis of symmetry, because it's going to be x is equal to 0 plus 3 divided by 2, or 1.5. I can then take that and plug it back in. So 4 times 1.5 squared minus 12 times 1.5 plus 3. So even though I got rid of that 3 to find these imaginary roots in red here, make sure we're using that original equation with the plus 3 when we're finding the y value. What we should find is negative 6. So therefore, the vertex is 1.5, negative 6, and it is a minimum point. Again, it opens up due to that a value of 4. So try to do number 6 on your own. Try to go through and solve and find the vertex using partial factoring and find out whether it's a maximum or minimum by looking at the a value. Again, recommend pausing the video and we'll come back with the answer. So coming back, we should be able to cancel out the minus 2, set it equal to 0. Common factor, so we get negative 3x times x minus 3. We set each factor equal to 0. We get x equals 0 and x equals 3. This gives us an axis of symmetry of 1.5, which when we plug back in, we get a y value of 4.75. So our vertex is 1.5, 4.75, and it is a maximum point or a maximum value because our parabola opens down due to the a value of negative 3. So those are examples of how we can find the vertex, and I will take a quick look or give you a quick demonstration of why this partial factoring works, why we cancel out these x values to basically, or the constant to find these imaginary roots. So if I pull up Desmos here, let's type in a one of these equations. Let's go back up and we'll take a look at an easier one. So let's say x squared plus 2x minus 6. So I'm going to zoom out a little bit so we can see it. So I can see my graph here. I'm going to plot the axis of symmetry as well. X equals negative 1. So I see my axis of symmetry here. And I can see my parabola. Let's type in another equation, x squared plus 2x, and we'll say minus 10. Actually, maybe not minus 10. Do say minus 4. What do we notice? Let's do another one. X squared plus 2x plus 3. X squared plus 2x plus 5. What do we notice about all of these parabolas, right, or quadratics? They all share the same first two values, but what happens with the different constants? They have a different y-intercept, but we should notice that it doesn't really matter, right, what the y-intercept is. They're all along the same axis of symmetry. So if I was to let's get rid of all of these. And I'm just going to type x squared plus 2x plus c. And we're going to add a slider for c. So I'm going to change my c value. So by changing the c value, all it's doing is changing the y-intercept, and it's moving my parabola up or down along the same axis. So even if, right, let me get rid of this, let me get rid of some of these. So just showing you again, the axis of symmetry stays the same regardless of what the c value is. So if I go all the way back up, this was my original one, and I said, okay, let's get rid of that constant, x squared plus 2x. Right. I found my two roots, right, of -2 and 0, found the axis of symmetry. Now, these two roots of -2 and 0 are not the roots of the actual parabola that I was dealing with, right? I was dealing with the one in red. We can clearly see that those are not, -2 and 0 are not the roots of that parabola. That's why we call them the imaginary roots, because they're not the roots that we're dealing with. They're not the actual roots, but they are, those 2 points are equal distance on either side of the axis of symmetry. So we can use that to help us find the axis of symmetry, which is shared with the parabola that we're dealing with, the one in red, and then use that to plug it back in to find our vertex. So that's kind of the property that allows us to cancel out or get rid of the constant and still be able to find the correct vertex. So that's just some extra information. Hopefully it helps you understand why we can kind of use this partial factoring, or how this partial factoring works, or why it's allowed to work. Again, you could use partial factoring, you could use completing the square. Each is fine. They both still give us or allow us to find the vertex and determine whether it's a maximum or minimum. So again, so again, those are just some different examples, some different scenarios that we might come across. Again, the idea is just make sure you're comfortable using either method to find the vertex and determine whether it's a maximum or minimum value.